I'm needing this help, guys.
And that was Ocean of Color by Phillip Westley. And moving on into the planets, we have Gustav Holst coming up, beginning with Jupiter. And here we go. Play a Lion and Healy Prelude Lever 40 harp. So I'm going to check my levers. That one's Jupiter. And now we're going to go to another world, quite hot actually. We're coming up to Venus. Here we go. Here's Venus. pulsed from the planets. Okay, now we're going to come up to Phillip Westley again, and we are going to play Equestrian Dreams by Phillip Westley. Okay, here we go. It's at 7:30. It's 7:30, isn't it?
About 2 minutes.
I have 2 minutes.
Yeah,
Okay.
you got something you can throw in 2 minutes?
Sure, I'll do maybe I'll try Kathleen.
Ah,
We were still on Ocean of Color. Let's see.
thank you so much, Kim. That is really great. And a fine note to end up on. It sort of sounds Mayish, like
Yeah.
for our May meeting.
We went from what is it? April showers to May flowers.
Well, in California, we aren't having much of either, so it's good to have it at least in music.
Oh, thank you so very much, everyone. Thank you for enjoying. Thanks so much.
Yeah, thank you. And welcome everybody. This is the May meeting of the Orange County Astronomers. We're really glad that you're here. I'm Barbara Toy. I'm the president of the club currently. And we have a great lineup tonight. We're going to actually learn how to pronounce, I think, a word that I have seen many times and really appreciated. And I'm looking forward to that, as well as learning more about it. So without more ado, I will turn it over to our announcement crew, Kyle and Cecilia.
Thank you. Here we will get started. So I think Cecilia will start tonight.
Hello, welcome all new members. Thank you for joining us. We hope you enjoy this amazing meeting that we made for you.
Okay, so I'll just quickly do this. That the ANZA site is reopening, and the first star party of the season will be held on May 28th.
Okay, so star parties still to be determined, and things are getting better, as you can see, and summer's coming up. I know you guys are itching to get together. Still being cautious. The beginners class still online. And the next board meeting is May 15th. So it's around 2 days ago, 2 days to go. So if you guys need anything, look at the calendar, please, to see if any changes are there or any questions.
Okay, so for upcoming events, the Carnegie Observatories is hosting a lecture series. It started in April, but continues into May. It's in person and online. If you are interested, there is an Eventbrite link below, and I'm sure you can search it online as well.
Yeah, that event that Kyle is mentioning is amazing. If you haven't already gone, it's at the Huntington Library, and there's live music at the beginning. Like our wonderful Kim here, they have a violinist and a piano player, depending on the days. And so the first half hour, it's lovely, just kind of, you know, meditating into the meeting, and then it begins. So if you haven't already done so, I'll see you all there next time. All right, so for Owens Valley, we actually are going to Owens Valley, right, guys? Because we're excited. It's going to be June 24th, 25th, and week 6 to 26th. There'll be pizza. There'll be climbing that dish. There'll be some students. And from what I know, Rest is going to join us from across the world. Yep. We're going to do a live interaction teaching across. So it'll be the first time that we're doing outreach live across other parts of the world. So it'll be one for the books. If you guys are interested in going, please come with us. We would love to have you. Dr. Miller is the contact info, and we'll hope to see you there. It's free, of course. Just you get yourself there in Bishop, and we'll see you there.
This is another event coming up at Mount Wilson, the Summer Observational Astrophysics Retreat. If you're interested, there is more information at the link, and applications are currently being accepted on a rolling basis until all slots are full. It's a 2-week intensive course at Mount Wilson.
Outreach coordinator will be this person here. Luckily for us, it's summer, school is over, most people are already out of school. So we're getting a break of outreach, and also the whole pandemic's kind of went, you know. So we're already booking for next fall. People have been already getting to us and asking us for summer events. So look forward to August events, all of you that are eager to go out there again. We have you in the books. Most of you already volunteered to call us in. If you have new volunteers out there, especially the new members, please join us and bring your telescopes out there, and it'll be a chance to practice, because if you never had a telescope before, that's cool. Children won't know the difference, you know? Look at the moon. It's fine. And I think they're just odd to meet people in the, you know, with the telescopes. Sometimes when we go out there, we do have technical difficulties, or it gets clouded out, and they say, no, stay. And it's just to see a telescope. For them, it's like a great thing. So those of you that have been there, you know what I'm talking about. If you haven't been there, it's not too late. I'll see you in August. Please go ahead and reach out to us at outreach@OCAstronomers.org.
Hello, my name is Galileo. Today's moon is gonna be a waxing gibbous. Hopefully you guys see the beautiful moon today, and have a good night.
All right. The Adoptoscope program details are now live on our website, so you can find all the information you need if you are interested in acquiring a scope. So all that, this is just a snapshot of the website, but it's all there. You can see there's the current inventory and then the related agreement with that program. So if you're interested, please go to the website. It's under the resources tab and then adopt a scope. If anyone has any items of interest they would like to put into the Serious Astronomer newsletter, please contact Dave Fisher and he will review those items. Just a reminder for everyone about their newsletter delivery. Remember, everyone always gets a printed copy, but if you can choose to opt out of receiving a printed copy and only access it online, that is something you're interested in, please contact the club. It saves us printing costs if you don't want. So if you aren't going to use the printed copy, please do opt out. everyone always also has online access, so you can access it through the website. But if you want to opt out, please email Charlie. But again, everyone gets both digital access and printed access unless you opt out of getting one mailed to you. Please remember to clear your weeds at ANZA site. I think right now we shouldn't need an extra reminder about fire danger, but please keep everything clear. And then next will be the What's Up presentation. Thank you.
Very cool. May I leap in with excitement? All right. All right. Okay, time for a whirlwind tour around the sky, a little bit of what's up in the sky. First of all, if you've noticed, the days are getting longer and the nights are getting shorter. Of course, next month is the start of summer and the longest day of the year and the shortest night. That means your planning for what you're observing in the sky needs to be razor sharp because you have fewer hours to do it. Let me make some suggestions if I might. Let's start talking about the moon. We already had the report from Galileo, and thank you for that. It is indeed a waxing gibbous tonight, closing in on a new moon, a beautiful full moon on May 15th. And I do mean beautiful, and this is unusual because of something that's going to happen this full moon. Let me mention, if you want to see the moon in the morning sky, May 22nd is last quarter, and we're going to round out the month. May 30th will be the next dark of the moon. But back at that full moon, usually when the moon goes around the back side, it misses the Earth's shadow. Normally does, goes above it or below it. This time it's not missing. We're going to have a beautiful lunar eclipse where the moon will be plunged into the Earth's shadow at full moon on the 15th. Some detailed notes here from Griffith Observatory in this slide that you see. The moon will rise with the eclipse already started for us. Just the very, very first part of it. The moon will begin to touch the deepest parts of the Earth's shadow, the umbra, that darker section in the middle, right about 7:30 in the evening. Okay, so the moon will just be rising up, the sky will be getting darker, and you'll start to see that bite taken out of the moon as it gets in the shadow. Deepest eclipse is 9:11 p.m. And as you can see, this is not a shallow eclipse. This is a good, proper, deep, full lunar eclipse. Then 9:54, the moon's going to begin to exit the shadow, so just shy of 10 o'clock, and the moon will be completely out of the shadow at 11:51. So it's convenient hours for this one. This is very conveniently timed for all of us who maybe don't want to stay up till 3 or 4 in the morning. Lunar eclipse, May 15th, mark your calendar. It's going to look beautiful. It's nice and red. This is a photograph of a real one. But not the same one that we've got this time because it hasn't happened yet, and we believe in observing temporal conditions here. No photographs before they happen, please. Run down the planets. Mercury has already been noticed, if you watch the announcements, as being very low in the west at sunset. It's close to the sun. Not a good time for looking at it. It'll pass between the Earth and sun on May 21st. Venus, Mars, Jupiter, and Saturn are all morning objects. Slide to follow to give you an idea. They're in a similar part of the sky. Actually, they form kind of a train in the morning sky. Right now, there are no planets in the evening sky that you're going to notice. They're all in the morning sky. We'll show you where in a second. Uranus is just emerging from the sunrise in the dawn. It'll be better in a couple of months. Really pretty much invisible right now. Neptune is also a morning object in the train of planets in the morning sky. Pluto is also visible down in Sagittarius, but visible is with quotes around it. It is just slightly brighter than the object of tonight's talk. Oh, thing. You know what I mean. Pluto, dim, hard to see. Here's a meteor shower announcement. I don't normally do that, but this one's unusual. The Tau Herculid meteors. These usually are very, very faint, not much to them, but this year they think this might be a bigger deal. Notice, by the way, on the screen, you've got typical radiant in the constellation of Hercules. But this the outburst radiance actually in a little bit of a different place. It's kind of special circumstances. This shower was created from a comet, Schwarzmann-Wachmann 3, but it broke up. The comet broke up and is strung out into a bunch of clumps of debris. We think we may be relatively near one of the stronger clumps of debris. There may be more meteors. There's nothing to worry about. There's no danger from this, but make a point to look on the last day of the month. Maybe we'll get a surprise. 9 o'clock sky here spread out all around the horizon. You can see that beautiful moon that Galileo was talking about. It's down in one of my favorite constellations, Virgo the Maiden. I want to call attention to that. Let's look at the south. Virgo the Maiden here, this is a nice illustration from 1822. It hasn't changed much since then. It's still a perfectly good illustration. Of particular interest, the Harvest Maiden here, you may notice she is carrying a sheaf of wheat. The bright star Spica in that constellation doesn't mark her head, as you might think for the brightest star in the constellation. Actually marks something she's carrying, which is, of course, an important symbol of the harvest. Virgo right now is home to the moon, right near that bright star Spica that I mentioned. This is the time of year in the south where we torment ourselves by looking at constellations right over the beautiful southern constellations of Crux and Carina and all the ones we can't see. But there are some distinctive patterns down there I'm very fond of. Just below Virgo, you can see a four-sided, kind of lopsided box there of Corvus the Crow. Corvus the Crow is an easy constellation to find. And I'll be showing you a couple of objects in that those two constellations there. Here's galaxy M58. This is in Virgo. You may know there are a lot of galaxies out at this time of year, tons of them. We couldn't begin to talk about them all. This is just one example and one of the slightly more unusual ones that I don't usually show. Looking here at a chart, you can see it's just up above the stars of Virgo in the lower left and just below the stars of Leo, which are off screen to your right. There's a whole clump of galaxies there. M58 is labeled, but that whole big cluster of galaxies is the Virgo cluster of galaxies. There are lots of them that you could hunt there. It's kind of a map. It's a mob scene. It's like a mosh pit of galaxies. There are so many of them you could get lost. Let me make another suggestion real quick, which is the Sombrero Galaxy. This is also in Virgo, but it's on the border with Corvus. That's one of the reasons I mentioned it. Now, at the bottom part of the constellation, this beautiful galaxy can be found right off that little four-sided boxy shape of Corvus the Crow. It's almost in Corvus, but not quite. Looking to the north, we've turned around here. We're looking towards the hills where we can see, I'm sure, lots of forest fires burning. You can see Ursa Minor there, the label's upside down, but right below that is the North Star Polaris is there. The stars of Ursa Major are across the top of your screen, the Big Bear, and those stars are now going over the top. Ursa Major is a beautiful constellation to look at this time of year, but these are circumpolar stars. They don't set. For example, Draco the Dragon. Thank you, Chuck Edmonds, for pointing out it looks like a saxophone. Yes, it does. The mysterious and dim constellations of Lynx, Camelopardalis, even down on the low side, Cepheus and Cassiopeia are all technically up. These stars never set from Southern California. Looking straight up, we do have Ursa Major, the Great Bear. It could be a bear if it had a nuclear mutated long tail, or it could be a dinosaur, and the three stars in the handle mark the neck of a brontosaurus. That's my personal favorite. Leo the Lion there really looks like a lion who is just lion there. You can see Virgo with the moon in the bottom quarter. Constellation I won't talk too much about, but Otis the herdsman does have the bright star Arcturus. And there's a couple of faint constellations, Canis Venatici, the hunting dogs, and Coma Berenices. Not kidding, it's Bernice's hair. Leo the Lion is a beautiful constellation. You can see that striped dashed line diagonally running through it. That's where the sun goes during the year. So it's a zodiac constellation. There are planets that pass through this constellation regularly, encountering the star Regulus, which is the bright heart of Leo, but there are no planets in the constellation right now. Doesn't mean you should ignore it, because there are things like this. The yet more distant galaxies, billions of stars, M65, M66, and NGC 3628 in Leo. And these are actually one of my favorites because they're pretty easy to find. In the pattern of Leo, there's kind of a triangle of stars marking his back part. And you can see them there just below the center and slightly left on your screen, M65, 66. They are located right in the pattern, just below the pattern of Leo, easy to find. Jumping up to Ursa Major. Ursa Major is a major deal with the Dipper stars and all the rest of that, of course, known through cultures around the world. Everybody had something to do with these stars. Astronomers no different. We look at them all the time for lots of things like, well, here's not a galaxy, gas cloud blown off by a dying star, M97, the Owl Nebula in Ursa Major. Pretty darned easy to find. Good one to start with. You got a telescope right in the pattern of the bowl of the Dipper, marked and labeled there in blue. Then you've got yet more galaxies, the M81 and here M82 pair of galaxies located all the way at the other end of the constellation. I find these two by going diagonally across the bowl of the Dipper and going off to the north, and it gets you in the general neighborhood. This is one of countless galaxies in this part of the sky. Now looking at Canis Venatici and Coma Berenices, following these stars as they move across the sky. Here's a picture of Boötes. I didn't notice it until I saw this, but he has the reins on those two dogs, which are Asterion and Chara. Those two are chasing after the bear. You may notice a weird heart with a crown on it that marks the star Cor Caroli. It isn't anything to do with the legend of the hunting dogs, but an astronomer claimed in England that that star shined unusually bright the night after King Charles I was beheaded. So that's the heart of Charles, Cor Caroli. For object to look at in that part of the world, I'll show you in just a second, and you can see Coma Berenices. It is Queen Berenice's hair. I'm not kidding. It's just her hair. So we'll show you something in that. For famous objects in Canis Venatici, you need look no further than the famous Whirlpool Galaxy. And this one is a particular favorite because, again, it's very easy to find. It's right there off the handle of the Dipper. Last star in the Dipper, and you just drop slightly down. There are lots of others. Gosh, the Sunflower Galaxy I see on the chart. Can't talk about them all. In fact, let me not talk entirely about galaxies. My favorite kind of object is a globular star cluster here in our galaxy. These things are gorgeous. They look like spilled salt, so many stars. This one is in a slightly empty part of the sky, but basically if you draw a line between the bright star Arcturus in Boötes and Cor Caroli, see if they're at the top of the chart, then M3 can be found roughly between them. In Bernice's hair, we know what her problem is. She has NGC 4565 stuck in her hair. A beautiful edge-on spiral galaxy picture here from the Hubble Space Telescope. And that can be found. It's a faint constellation. You have to fish around a little bit out there, but it's well worth it if you're in dark skies and have a reasonably sized telescope. This was the 9 o'clock situation with Ursa Major at the high point. If you wait a while till 5 in the morning, you'll find out what I was talking about, those planets, right? Now Ursa Major is setting up in the upper right of your screen. And the three summer stars, the summer triangle stars, Deneb, Vega, and Altair, are overhead. If you look, there are a whole series of relatively bright marks that I've made there on the slide. Let me zoom in and call them out. I will note that Neptune is a marker. You need a telescope. That dot shows where Neptune is. Need a telescope to see that, but the others are all naked eye obvious things. Saturn is in Capricornus. Rings are beautifully tilted open to us now. Mars has gotten a bit brighter. It's an easy naked eye object. Then you've got Jupiter, and between Mars and Jupiter, you've got Neptune. Jupiter is the next brightest thing to in the sky, except for Venus and the sun and the moon. And Venus is the brightest thing in the sky, except for the sun and moon. So you'll have no trouble seeing this amazing train of objects in the morning sky. And that concludes a quick whirlwind look around the sky. And until the next time, I will wish you all clear skies. Thanks.
Yet another great presentation. Thank you very much, Chris. And I would like also to mention that since you brought up Griffith Observatory, They do live stream their event, right?
Yeah,
and
here
the
I forgot
eclipse.
to mention it. I'm so sorry. Everybody watch the Griffith live stream, by all means.
Sure, that's one of the great things about all these virtual things. So, hi everybody, my name is Reza and I'm the Vice President of the club. I too would like to welcome you to the May 13th, 2022 General Meeting of the Orange County Astronomers. And without any further ado, let me go ahead into introducing our speaker tonight. He got his PhD in physics from University of Illinois in 1998, and he has been a faculty at Arizona State University since 2003. He is the recipient of the 2003 Near Prize from Meteorological Society, and he is the namesake of asteroid 9926-. Please join me in welcoming Dr. Steve Desch. Steve.
Thank you. Oh, it's really quite a pleasure to be here. This is a fun meeting. I like the harp. I really enjoyed that presentation about the sky tonight. That's great. Which reminds me, I'm very excited about the Tau Herculids because it could be a dud or it could be spectacular. It could be a sort of once every second sort of event like the 1998 Leonids, where it all depends on whether Kamish-Fashman-Wachmann 3 erupted big enough in 1892, apparently. But that would be the night of May 30th going into the 31st. But I think that we in the Southwest would be really ideally suited to see it night of May 30th, 31st. So yeah, I'm gonna look. Well, yeah, so I'm coming in from Arizona and I live in Phoenix. It's a real pleasure to be here virtually. So I'm going to talk to you tonight about, let me try to share my screen. Let me apologize, it's Friday the 13th and Zoom and PowerPoint don't play well on my computer, but hopefully you're seeing the presentation now. So I want to talk to you about this interstellar object, Oumuamua. And this is what I'm going to try and convince you, the closest exoplanet we've ever seen. So you may have heard about this object in the news. It was discovered in October of 2017 by Robert Warwick using the Pan-STARRS telescope array. This is an array of telescopes on Haleakala in Maui in Hawaii. And in honor of that, it was given a Hawaiian name. The name itself means scout or messenger. And I believe the little apostrophe is the opina, that's the glottal stop in Hawaiian. And so it's Oumuamua. Let's go with that. So this was the first object that was confirmed to come from outside of our solar system, besides maybe a piece of dust or something. This is the first macroscopic big object that was coming in so fast that it had to be coming from outside of our solar system because it can't possibly orbit within it. And this was not unexpected. We knew for decades that we should be seeing objects like this, but we expected comets. And this was in some ways like a comet, but in other ways it was very not like a comet. And so it was instantly mysterious. And some of the mysteries about this object include the fact that it seemed like we found it pretty quickly, just within years of this Pan-STARRS array being operational. And so there must be an extremely large number, much larger than the number of comets that we expected to see. And it entered the solar system in a speed and direction that in some ways was unusual. I'll talk about all of this. It mostly orbited the sun according to the laws of gravity, but it did experience an extra little push. I say little, it was about 0.1% the strength of gravity. And it pushed away from the sun just a little bit faster than you'd expect if gravity alone were molding its orbit. And comets do that, but in other ways, this was not a comet. We didn't see any dust. We didn't see any carbon monoxide. We didn't see other things that we expect to see from a comet. Also, it had a very crazy shape. Its light curve showed that it varied in brightness quite a lot over the course of hours, which meant it had a crazy cigar or pancake shape that we haven't seen in objects in our own solar system. So there were a lot of mysteries about it, and nobody could figure out what it was. And work that I've done here at Arizona State with my collaborator, Alan Jackson, we think we put together the case that this is a piece of an exopluto, that what we're looking at is a piece of the surface of a planet just like our Pluto. If you were to take a chunk of nitrogen ice from the surface of our Pluto and throw it by the sun, it would do exactly what this object did. And moreover, we have every expectation that our solar system did eject quite a lot of fragments, the size and composition we infer for Oumuamua. And this would imply then that things that happened in our own solar system were common and happened in other solar systems. So let me get right into it and talk about all of that. So this is an animation showing the trajectory of Oumuamua as it came by the sun. I'm going to play this. And so it came in from above and encountered the perihelion distance closest to the sun on September 9th. And it flew by Earth, closest approach around October 7th, but we didn't actually observe it until the following week. Let me play that again. So it was already on the way out of the solar system. And several telescopes were looking at it by then, including the Spitzer Space Telescope, which observed it when it was over here at a distance of 2 AU in November of 2017. So that's a very important aspect, that this object was only discovered when it was very close to Earth and it had already gone by the sun. But it was definitely on a very hyperbolic eccentric orbit that is going to make it leave the solar system. It's been going through the solar system for decades and will take decades to leave. All right. Next slide. So if you were to watch it in the sky, and you would see it come from this direction, and what we're mostly seeing here as the Earth orbits, we see its perspective change. So this object was seen mostly in the direction of the solar apex near Vega, which I'll describe. That's important. And then it whizzed by the sun and was in constellation. Is that Leo? I think we're looking at Leo there. And then whizzed by Earth and is on its way out of the solar system in a different direction. So the solar apex is a very interesting direction. If you were to look near the constellation of Vega, we see that a lot of the stars that show some proper motion, that seem to be moving in our sky over the course of centuries, seem to be moving away from this direction. And that's because of our motion through the galaxy. And so if you were to look at our solar system from above the galaxy here, you would see that the sun and our solar system, they're all orbiting the galaxy. It takes about 220 million years to do so, and mostly moving in this direction. And the sun and other stars have, they're kind of caught up in this flow, orbiting the galaxy. But then the sun has another particular motion with respect to this sort of average. So if you were to look at the directions and speeds of all the stars in our vicinity, they are all moving around the galaxy at about 220 kilometers, about 200 kilometers, 240 kilometers per second, taking about 200 million years to go around the galaxy. And then on top of that, stars have these own random motions. And this is confusing. So what astronomers do is they define the average velocity of stars in our vicinity as the local standard of rest, or LSR. And every star in this neighborhood kind of orbits the galaxy with that speed, which is again like 250 kilometers per second. But then they have their own individual random motion with respect to that. And the sun moves with respect to the local standard of rest about 18 kilometers per second. So it's going around the galaxy at about 18 kilometers a second faster than the average star is. But some stars are orbiting a little slower, some are orbiting sideways, and they all have these random velocities. So that defines the local standard of rest. And stars appear to come from this direction, and this direction to the right here would be the direction of Vega. And they appear to come from that direction because the sun is moving towards that direction. And so Vega is more or less the direction the sun is moving with respect to the stars in our neighborhood. So what we see is that Oumuamua actually came from that direction, and it was actually moving a little bit faster towards the sun than its velocity. It was kind of moving in the opposite direction with respect to the local standard of rest. And it was doing so at a speed of, it's kind of hard to pin it down, but around 9 kilometers per second. So those combined speeds, it means it entered the solar system at about 26 kilometers per second. And then that speed added to the speed it gained when it went by the sun. It was actually going 80 kilometers per second at perihelion, and then it's leaving the sun and slowing down, and it'll leave the solar system at a speed of about 26 kilometers per second, but in a different direction. All right, so all of this kind of makes sense. What's unusual about this speed is that Oumuamua was moving only 9 kilometers per second with respect to the local standard of rest. Most stars move at around 20 or 30 kilometers per second with respect to the standard of rest. And so it was perceived as unusual that it's kind of moving so slowly with respect to the average velocity, although I'll show you it's not really that unusual. But that was the perception at the time. All right. One of the weirdest things about Oumuamua, though, was the shape and the light curve. So if you were to measure the brightness of Oumuamua as it spun and rotated, what you'd find is that it was magnitude 22 sometimes, and then a few hours later, magnitude 24, 25. So these are extremely dim objects. This is like orders of magnitude dimmer than even Pluto. It's a wonder we saw it. But is the change in brightness. This is a very big change in brightness to happen in only a few hours, and then it would get bright again. And it was sort of quasi-periodic, and these are a number of telescopes that observed it. So this deep minimum requires it to change its orientation and to have a very elongated shape. It must be either a cigar or a pancake shape so that it can spin and present a very small cross-section to you sometimes and a big cross-section other times and reflect a lot of light. The first model that was tried involved a cigar shape, and that was found to kind of work. But then, I don't know, a few weeks later, somebody says, well, maybe a pancake shape would work. And they found that actually works and is more probable and makes more sense. So a pancake shape is sort of the established shape with axes that are 6 times wider in these directions than its thickness. But a cigar shape with a 10-to-1 axis was also considered first. And unfortunately, that got into the popular press right away. And so everybody considered it to be a cigar shape. Although if you look at this cigar shape, it could just be a pancake edge on. That tells you how it's sort of hard to tell the difference. But it spun around every 8 hours and maybe was 60 meters in diameter, which is really not that big. And it was probably pancake shaped. Whatever the shape was, there's no objects in the solar system like of this size that we know of that are this elongated, that have this extreme in axis ratio. So that was immediately a big mystery. How did this happen? All right, let me get back to that speed. When it was at perihelion, which was at 0.25 AU, which by the way is inside the orbit of Mercury, it was moving at 88 kilometers per second. And like all objects, it was slowing as it left the sun, as the sun's gravity tried to keep it from leaving the solar system, but it still has excess speed, so it is. And it was decelerating at about 0.3 centimeters per second squared. This is 1,000th of the Earth's gravity, for example. So it was decelerating as it left. However, like a lot of comets, its deceleration was slightly less than gravity alone could explain. And this commonly happens with comets because of the rocket effect. So this is an image of the Comet 67P imaged by the Rosetta spacecraft. And you can see that the sunlit side has all this gas streaming off of it. And that's simply because the sunlight is heating and sublimating the ices in this comet. And they leave at pretty close to the sound speed, but only from the sunlit side. So of course, they're pushing off the comet, and the comet is pushed away from the sun by this effect. And this happens due to sunlight. And so as you'd expect, this effect gets weaker the further away from the sun you get. It more or less varies as 1 over the distance squared. And just like comets, Oumuamua's acceleration also varied as 1 over the distance squared. So actually there was really little mystery about this deceleration. But the only mystery is that the acceleration was about 10 times stronger than comets typically experience, and it could not be explained by sublimation of water ice. And so that was a bit mysterious. In the popular press, if you heard about this non-gravitational acceleration, it sounded like a bigger deal. It almost sounded as if this object took a right angle turn and made a beeline to Earth or something. It did nothing of the sort. It just pushed away from the sun a little bit stronger than comets do. Nevertheless, that couldn't be figured out immediately at first. One of the other mysteries. So compiling all these mysteries, here it is. There was a list that was made by Bialy and Loeb in 2018, and they they listed all these mysteries. I'm going to list them here and then get back to them at the end to show that they're not so mysterious. But basically, the mysteries boil down to, we saw this one right away. That means there must be quite a lot of these objects, way more than we expected. There must be about 10 to the 16 objects like this per star, or, well, that was the first guess. More careful analysis maybe says 10 to the 14 to 15 objects per star, but still that's a lot of objects per star, because we expected only something like 10 to the 12 or 10 to the 13 comets have been ejected from our solar system, and would have been ejected from other solar systems. So it's orders of magnitude more abundant than that, but probably they're just not comets. It was moving with respect to the local standard of rest at a sort of slow speed, 9 kilometers per second, slower than the typical 20 to 30 kilometers a second stars move with. There was that crazy axis ratio. And just for comparison, most objects in the solar system, including fragments of asteroids, don't have an axis ratio bigger than 3 to 1. There was the non-gravitational acceleration, and I didn't mention it, but Spitzer Space Telescope observed it, and we could tell there was almost no dust, very, very little dust, way less dust than a comet would typically have, and there was no emission seen from carbon monoxide, water, carbon dioxide, certain other key gases that comets would typically have at the more than a few percent level. And we would have detected them if they had typical cometary compositions. All right, so those are the mysteries. Once these mysteries were established, boy, people tried to figure out what it was and how it could have been ejected from its solar system. If it wasn't a comet, then what was it? And some of the proposed explanations included asteroids that were tidally stretched as they went by their sun and somehow ejected, although there's a lot of details in any of these. That was just one idea to explain one aspect. The elongated shape, most people realize that if you start with something that's non-spherical and erode it, like this diagram shows a non-spherical fragment of an asteroid, as it gets eroded by, say, collisions with dust grains, gets sandblasted, and a uniform thickness is removed from every part of it, you'll find that it becomes smaller, obviously, but more elongated, like the axis ratios are magnified. So this is definitely a mechanism for turning something that is slightly non-spherical into something that is very non-spherical. But nevertheless, you have to identify a mechanism. People were thinking maybe ultraviolet radiation if it were ice, or dust grains, but none of these really worked out. They couldn't explain the magnitude of the effect. I won't even go through this slide. Just suffice it to say, there were lots and lots of explanations to explain a lot of these aspects. And as for the non-gravitational acceleration, it was recognized that it could be ice, but this paper by Seligman and Laughlin proposed hydrogen ice, which, by the way, would require temperatures below 2.8 Kelvin to even form H2 ice, and you couldn't form an object this big even if you tried. So I don't think it's a very viable theory, but at least it is a natural substance. Other ideas that were proposed were solar sail by Logan Bialy. They suggested this was an artificial construct. And in fact, Avi Loeb wrote an entire book arguing that it had to be, because he couldn't possibly imagine what else it could be, which shows a lack of imagination, in my opinion. But as I said before, the cigar shape that was inferred for it immediately reminded everybody of Rendezvous with Rama by Arthur C. Clarke. And so it was really natural for us to think about spaceships. But my co-author and I felt it was really important to exhaust all possible natural explanations before we go there. So we started to investigate what could this object be, what natural object might it be. So we started with this aspect, that this careful modeling of the light curve by Meshchenko showed that it was probably a pancake shape with these sizes, 113 meters this direction, 111 meters this direction, 19 meters this direction. If its albedo, if the fraction of sunlight that it reflects was 10% or 0.1. And we began to realize that everybody was assuming a very low albedo for this object. They were assuming it was very dark as asteroids, because there was this perception that if it was not a comet, because they didn't see water, they didn't see dust, that it must have been an asteroid and therefore dark. And then it was very hard to explain the acceleration. But we began to realize that if you assume it's ice, then it's going to be very shiny and reflect a much greater fraction of the sunlight hitting it. And that actually immediately explains a lot about the acceleration. The amount of sunlight that it actually encounters, if it's very shiny and bright, is going to be smaller. It actually encounters less sunlight. And that's because if it is a certain brightness, we know its brightness, and it's very shiny, it must not be very big. So it must reflect a lot of sunlight. However, the rocket force is going to be proportional to that. It's going to be proportional to the method absorbed, which is 1 minus p, times 1 over the albedo p. So that will be affected. And generally, brighter objects will feel less force. But remembering, high school physics, force is mass times acceleration. So the acceleration, which is actually what we measured, the acceleration, that's equal to the force divided by the mass. And when you're talking about a small, shiny object, the mass actually is a lot less and is going to scale as the albedo, the minus 3/2. So the acceleration actually gets bigger the shinier it is. So it's actually reflecting a smaller amount of sunlight, but it's getting a larger acceleration if it's small and shiny. And so we immediately realized, if you're looking at ices, that maybe this is why it got such a bigger acceleration. And we did a lot of calculations. This is from, we did 2 papers. This is from the first paper. We rederived the rocket equation. What acceleration do you get if you are sublimating ices on the surface of a cometary body? And a lot of the inputs into this, like the heat capacity and the sublimation energies of ices, we had to compile from the literature. And this is the table from the paper. And there's a lot of literature. A lot of it goes back to the 1800s, which was kind of fun. But yeah, depending on what ice you put in, you get different numbers to put into this equation. It's going to look more interesting in this plot. So this is a plot of the acceleration we predict in units of the acceleration that was observed. So obviously we want to get to 1. That's the acceleration on this axis. And on this axis is the albedo, which we're just going to leave as a free parameter. Most comets and asteroids would be down here, very dark objects. But we are imagining that it could be very shiny. And depending on what the composition is and how shiny the object is, you get different accelerations. So we confirmed the result other people found, that water ice will never, no matter how shiny it is, it's never going to get you in the neighborhood of 1 times the needed acceleration. Carbon monoxide would, but it is ruled out because the Spitzer Space Telescope would have seen it. Same for carbon dioxide, if that were to work. These other ices, we don't see them. Methane would be great. We see that, but it's a very rare ice. Neon ice, I don't think we'd see that. Hydrogen ice, if it existed and the object was either very shiny or very dark, actually this curve comes back here, would give you the right amount of acceleration, but in fact, it's just too good of an ice. It just boils off so fast from an object that it'll never work. But we found that nitrogen ice is one of these ices that would work if the object were made out of nitrogen ice and the albedo were 0.63 or so, reflects 63% of the sunlight hitting it, then we would get exactly the acceleration we need. And what's wonderful about that is that nitrogen ice is actually observed in our solar system on the surfaces of Triton, Neptune's moon, and especially Pluto. And on those objects where nitrogen ice makes up 97% of the surface material on Pluto, the albedo is in this red range. And for Triton, it's in this range. So if your object is made out of nitrogen ice, you get exactly the acceleration we observe if its albedo is exactly what nitrogen ice is observed to have on the surface of Pluto. So this to us cinched it. And once we had this idea that basically we're looking at a chunk of frozen N2, like the air in this room, but frozen nitrogen ice that looks exactly like the ice on the surface of Pluto. Everything else sort of fell into place. So we could calculate the distance from the sun as it went by, and this is on this axis days before and after perihelion, and we observed it at time 0 here. As it went by the sun, obviously it got hotter. Amazingly, it did not get above 50 Kelvin, even though it's inside the orbit of Mercury. It didn't get hotter than 50 Kelvin, which is like the surface of Pluto. And the reason is evaporative cooling. I live in Phoenix. We have a swimming pool. It could be 110 degrees out. I get out of the pool wet. And for that first minute, while water's evaporating off of me, I'm actually shivering. I'm so cold, even though it's 110. Same effect here. The nitrogen ice is boiling off so fast, it actually cools the body and it maintains a temperature below 50 Kelvin. However, it is boiling off nitrogen ice like crazy. And so this is the mass we calculated for the object before and after rounding the sun. And it lost about 90% of its mass by going by the sun. And so it started as an object that maybe had an axis ratio of 2 to 1, but after going by the sun, its axis ratio is closer to 6 to 1. And this explains just about all the observations about the shape and size of Oumuamua. And especially, of course, the non-gravitational acceleration. These curves reflect the acceleration that it was observed to have at different times, actually. It's not just an average, but on different days they could measure the accelerations. And the red is our model. So it's right in the ballpark of what the observation suggests. So we think this settles it. And basically we're looking at the surface of a chunk of material from the surface of an object like Pluto, but obviously not our Pluto because it isn't bound to our solar system. It must have come from outside of our solar system. So we're looking at an exopluto. And I just want to remind you, thanks to the New Horizons mission, we see the surface of Pluto and it's covered with nitrogen ice all over. Here it's nitrogen ice plus some gunk, probably photolyzed methane turned into something called tholins, but everywhere is kilometers deep nitrogen ice, and especially in Sputnik Planitia, there's pure nitrogen ice glaciers. There's a little bit of CO, there's a little bit of methane, they're at the less than % level. Now, it's very interesting that we only observe nitrogen ice on the surface of objects like Pluto, Triton, basically large dwarf planet-sized bodies. We actually don't see N2 on comets, and people have looked for N2 ice on comets for a very long time and never found it. These new observations of Comet 67P by the Rosetta mission have, I think, resolved the mystery in the last 2 years. And where they see the nitrogen is in the form of ammonium salts. It's kind of crazy, but comets do have the sort of typical amount of nitrogen we expect ices in the solar system to have, but it is in the form of ammonia or ammonium salts, and only 3% of it is N2. However, comets, this material that gets into a Pluto-sized object, Pluto-sized objects have subsurface oceans, and that nitrogen is easily converted into N2 gas in the oceans of these bodies, and then it will bubble up and come onto the surface of objects like Pluto. So it makes a lot of sense that that we do see N2 ice on the surface of Pluto's, even though we don't see it on the surfaces of comets. But that's a key distinguishing mark here. That if we see N2 ice, it's probably coming from an exopluto and not just some sort of comet thing. And that speaks to the origin of Oumuamua. Yeah, here's Triton, also has a lot of nitrogen ice, equivalent to several kilometers deep. How do we turn this ice, though, into chunks of ice, especially this large number, 10 to the 13, 10 to the 14 chunks of ice? And to understand that, we have to look at the history of our solar system and think about our Kuiper belt and the objects that exist in the Kuiper belt. I've mentioned that we have Pluto, we have Eris, Haumea, Makemake. These are all some of the largest dwarf planets. Triton counts as one. It just happens to be orbiting Neptune. Pluto definitely has N2 ice. We think Quaoar, Eris, Makemake also have N2 ice. it seems to be a common thing, as we'd expect if it's formed by reactions of nitrogen with water in these subsurface oceans. So the mystery isn't how you get N2 ice on the surface of an object, but how do you make so many chunks of this? And yeah, I keep getting ahead of myself. If we wanted to estimate how much nitrogen ice there could be on the surface of a Pluto, you have to imagine first that it would have gotten warm from radioactive elements inside of it, and it would have formed a rocky core, and the ices would have floated up, and it would have continued to warm, and the water ice would have melted and formed a subsurface ocean. You would have had water ice on the outside of that, and then any nitrogen N2 that's created in this ocean by reaction of like ammonium with other substances would have bubbled up and formed an N2 ice crust. When we look at the abundances of nitrogen in ices generally, we calculated that like 30 kilometers, 35 kilometers thick on the surface of Pluto. And even an object like Gong, which is one of these Kuiper belt objects with half the radius of Pluto, 600 kilometer radius, it could also undergo the same process and have an ice layer, N2 ice layer of 18 kilometers thick. So, probably any number of these bodies could have had nitrogen ice, and it's not easy for it to survive to the present day. Pluto's big enough; it has a lot of N2 ice still, but only kilometers left. But it would have evaporated from these smaller bodies. But bodies as small as Gong could have had these crusts of nitrogen ice. They would have had oceans and nitrogen ice. Smaller bodies, maybe not, but certainly in this size range, we would have. So how much ice are we talking about? How do we make chunks of it? And how does this escape the solar system? And if we understand our own solar system, the hope is we can understand how other solar systems would have ejected such objects. So one thing to remember about our solar system is that it underwent a lot of evolution in its first probably 50 to 100 million years. It probably did not form with the planets in the current configuration. This is a really profound theory that started to be understood around 2005, and I think is now accepted, that our solar system did the following sequence of events. So instead of Jupiter, Saturn, Uranus, and Neptune forming between 5 and 30 AU, and AU is the distance between the Earth and the Sun. So Jupiter is at 5 AU today, and Neptune's at about 30 AU. Instead of them being formed between 5 and 30 AU, they probably formed between 5 and 15 AU. So these check marks are supposed to denote every 5, 10, 15, 20, 25, 30 AU. And moreover, there was probably a disk of planets or dwarf planets and comets, Plutos and comets, that sort of thing, between 15 and 30 AU. And the total mass in all of these things was probably about 35 Earth masses. So you have, this is the starting configuration. After the planets formed, this is what we had in our solar system for the first 50 million years or so. And you'll notice the planets were probably switched in order. Uranus was probably the furthest planet out for a while. This collectively is called the Nice model, named after the observatory in Nice, France, where it was developed. So according to this model, Uranus being the furthest one out, its gravity affected the orbits of all of these planets and comets and scattered them and caused them to change their orbits and go into the giant planet region. And they would get gravity boosts every time they did. And one of the aspects about gravity boosts is that a planet can eject a comet or an asteroid into a higher orbit, in which case the planet loses energy, or it could actually send it inward, in which case it would gain energy. But all of these planets and comets zipping back and forth between the giant planets allows the giant planets to exchange orbital energy and angular momentum. And over millions of years, what's likely to happen is that Jupiter on average will migrate inward and the other 3 planets will migrate outward. The reason for that is that these objects are not generally massive enough to send a comet out of the solar system entirely. If a comet goes by Jupiter, though, Jupiter can eject it from the solar system entirely, and probably did eject quite a lot of comets. And when it does, the last time it sees one of these comets, it sent it out of the solar system and it moved inward. But the last time one of these planets saw a comet is when it sent it inward to Jupiter. So on average, they move outward. So this process went on for millions of years. And as Jupiter moved inward and Saturn moved outward, there reached a time where Jupiter and Saturn were in a 2-to-1 resonance, where Jupiter orbited exactly twice for every one Saturn orbit. That's a very unstable situation, because every time Saturn ends up back here, there's Jupiter. It's gone around twice, but there they are. And the gravitational tugs from Jupiter keep adding up to Saturn. That makes Saturn's orbit very eccentric, elliptical. And then it starts to interfere with the orbits of Uranus and Neptune. They start to have crazy orbits. They actually probably had a close encounter and they switched places in the solar system. Meanwhile, they're scattering all of these Plutos and comets. It's a mess. And this process probably played out in about 10 million years, about 50 million years after the solar system formed, all of it almost 4.5 billion years ago. The net effect is that a primordial Kuiper belt here, this belt of comets and asteroids and Plutos and things that existed at the birth of the solar system was depleted. We have only like 1 out of 1,000 of those objects left today. But the effect they had was to change the orbits of the planets. And of the objects that went by Jupiter that were lost from the primordial Kuiper belt, about 80% of them were ejected from the solar system entirely, and about 20% of them went into these really big orbits that now populate what we call the Oort cloud. And Neptune's migration outward probably sculpted the rest of them, gave them particular orbits that we recognize in the Kuiper belt today. The Oort cloud, I just want to mention, is this belt of comets, not even a belt, a sphere of comets that extends all the way out to about 1 light year from the sun. These are extremely distant objects, and there's probably about a few trillion, a few times 10 to the 12 comets in this Oort cloud, which means that about 10 to the 13 comets were ejected during this process. But for our purposes, the implication, it's well accepted that there used to be thousands of times more objects in this primordial Kuiper belt, including about 2,000 objects the size of Pluto. Pluto is just 1 or 2 survivors of its size, and 6,000 objects the size of Gongon. And all of this happened at the beginning of the solar system, and after that, it looks like the solar system today. All right. So what this means is during this process, when there were a lot of thousands of Pluto-sized objects, 6,000 Gongon-sized objects, and all of these objects sent on crazy orbits, there must have been a lot of collisions. And one of the fun aspects of this is that nobody really considered how many fragments would have been generated during this process. Well, we calculated this. Every Pluto would have been pummeled by about a Vesta, that's one of the largest asteroids, about that much mass of material, but in small things. It was basically sandblasted. And about a few thousands to about 0.05 Earth masses of fragments would have been created in the Kuiper belt, and a fraction of that would have escaped the solar system. Every one of those fragments that got ejected from a Pluto would have gone in orbit around the sun, and eventually some of them, like comets, would have been ejected from the solar system. So we calculated, how much every impact would have generated in terms of fragments. Most of the fragments would have been 100 meters in size, and adding it all together, something like 10 to the 14 ice fragments would have been ejected. Some of them get down into the water ice bedrock. Some of them are just pure N2. About a third of them are end up being N2 ice, and about 2/3 that escape are water ice. Anyway, a lot of fragments, and this is a very natural thing that should have happened in our own solar system, almost certainly did happen, and would have ejected just an enormous number, 10 to the 13 to 14 N2 ice fragments of the size of a Momo into interstellar space. Once they're in interstellar space, cosmic rays will erode them, and they won't survive more than about 500 million years, but they will survive for a long time. If an object like Oumuamua was ejected about 500 million years ago, it would have gone from a typical fragment access ratio of a little less than 2 to 1 to something like what we think it entered the solar system with. So we can't prove that Oumuamua itself was eroded by cosmic rays, but it could have been, and we think it's likely that it was for about 500 million years before it came to our solar system. So let's get back to that list of mysteries. So we now have this hypothesis that it's N2 ice. We think it would be very natural for our solar system to have ejected N2 ice. And if other solar systems ejected N2 ice fragments from exoplutos the way ours did, could this solve the mystery? So first mystery, like there are 10 to the 14, 10 to the 15 objects per star. This seems like a lot. Is this something that could have happened? Because again, our solar system probably only ejected 10 to the 13 comets. Well, yeah, given the amount of mass that we calculate, and basically, yes, you could have ejected a considerable number of objects, as well as 10 to the 13 comets, which is important because the year after Oumuamua was discovered, the second, and so far, these are the only 2 interstellar objects, but the second interstellar object to be discovered was the comet 2I Borisov. And this comet came into the solar system with hyperbolic orbit. It's definitely from outside our solar system. It looks a lot like a comet from our solar system though. And so this must be something that happens. But the fact that we have one of these small objects and one of these large objects means that the statistics have to work out. But the fact that Borisov is a comet, it was seen by an amateur astronomer while it was still 3 AU from the sun. Whereas Oumuamua is this tiny thing that needed to be very close to Earth for a sophisticated array of telescopes to see. It turns out very roughly those statistics work out that, yeah, we'd expect to see that many comets, that many fragments. And so we feel it all kind of works out. Oumuamua can't be something that we would observe well with the Pan-STARRS more than once every 10 years or so, but that seems to be about right. So I think the statistics work out. What about this thing about moving with respect to the local standard of rest of a slow speed, 9 kilometers per second, whereas most stars move at about 20 to 30 kilometers per second. If an object is coming from a star, the implication is it should be moving pretty fast. It would be a very unusual star that moves so slowly with respect to the average. But in fact, that's actually not really true. If you were to color code the stars in the vicinity of the sun according to the age of the star, what you'd find is that the old stars move really fast, but the young stars actually don't. They move really slowly. Typically, the speeds of stars younger than 2 billion years are about 6 kilometers a second. And the same is true of molecular clouds, which is where young stars form. So what's going on is that molecular clouds kind of move with the average speed. Stars that form from molecular clouds move with the average speed. And it's only after they've been around the galaxy a few times and have encountered other stars and had gravitational slingshots do they start zipping around faster. Our sun has gone through this stage. We are post-adolescent, and so we're moving at about 18 kilometers per second with respect to the local standard of rest, but young objects don't. So the implication is simply that if you formed Oumuamua in a young star system and ejected it before it was 2 billion years old, and it's been moving through the galaxy for less than 2 billion years, then it should naturally have a slow speed. So that totally makes sense, because if it happened the way it happened in our solar system, Oumuamua would have been ejected during the first 50 million years, way younger than a 2 billion year age. And we think it was probably only in the galaxy less than 500 million years, not even 2 billion years. So it should have a very low velocity with respect to the local standard of rest. That crazy shape, the axis ratio, totally explained if it lost a lot of mass, something like 90 to 95% of its mass as it went around the sun. it would have been really nice if we could have observed it before it encountered perihelion with the sun. It would be great prediction to see if we have other nitrogen ice fragments and see if they're less elongated if we catch them before perihelion. But according to this hypothesis, it really should have a very elongated shape. So it totally makes sense. And we think, though, it needed a little bit of sculpting in the interstellar medium beforehand. Not necessarily, but we just think it's kind of likely. And so we kind of infer that it was traveling through the solar system and eroded by cosmic rays for about 0.4 billion years, which means it was traveling for about a distance of 3.6 kiloparsecs. And so we just see a lot of consistency if it was actually coming from a young star system, again, a newly formed star system in the next spiral arm in the galaxy, in the direction of Vega, and this would be the Perseus arm. And if it were in the Perseus arm and then traveling towards us for about 500 million years, a lot of things would fall in place. Although this is not something we can prove, it's just kind of speculative. But that's my best guess, that this object was ejected 500 million years ago from a newly formed star in the next spiral arm over the Perseus arm. And then the non-gravitational acceleration is very well explained, as I showed you, if it's N2 ice. And the Spitzer infrared observations, yeah, we wouldn't detect the amount of CO or dust or CO2 that we'd expect if it's the surface of an exopluto, because there's just not that much and we haven't observed it. So one corollary, though, before I finish here, is that if there were fragments of Plutos created in our own solar system, and most of them are ejected, but not all, if 20% of them just go into the Oort cloud, then we should expect to see about, well, some fraction of long period comets that come from the Oort cloud to resemble the surface of Pluto. Not many would survive 4.5 billion years of cosmic rays in our solar system. Our solar system is 4.5 billion years old, so cosmic rays would have destroyed most nitrogen ice fragments, but the very few very large ones might survive. So is this prediction held up? And there is this one unusual comet, and it seems that there might be some others like it, but out of the hundreds of comets that have been characterized this well, this is really unusual. Comet 2016 R2, it's already been identified to be very reminiscent of the surface of a differentiated Kuiper belt object like Pluto. There was no water detected, no OH, no sulfur species, very little dust. These are things that you really expect to see from comets that are universally seen. This object, we didn't see it. It did have a lot of CO ice, which Pluto itself does not, but is something that condenses at similar temperatures to N2 ice. And it definitely had N2, and in fact, an unusually high amount of N2, because it's very hard to find N2 in most comets. But its N2 to HCN ratio, it was 10,000 times what other comets have. And it was kilometers in size. So it's a very, very likely that this object is the closest thing in our solar system to what Oumuamua is, and about 1 in 1,000 comets, maybe something like this, and have survived 4.5 million years in our solar system. So to sum up, this mysterious object, the first interstellar object, first object known to come from outside our solar system. At first it was very mysterious, but a chunk of N2 ice, like we see from the surface of Pluto itself, passing by the sun is consistent with everything we know about this object. And this would be a likely thing to happen if other solar systems were ejecting at least as efficiently as our own solar system. Our own solar system almost certainly ejected 10 to the 14 or 15 fragments of nitrogen ice from all these collisions between the Plutos and other objects during the earliest stages of our solar system. To make the statistics work out, we kind of need other solar systems to be a little bit more efficient than our own solar system by about an order of magnitude. But actually, we expect that low mass stars would be really good at ejecting, their planetary systems would eject orders of magnitude more into ice. That's an area of active research right now in my group. But clearly, this is something that happened in our solar system, gets you in the ballpark of the right numbers, and all the aspects of Oumuamua itself are consistent with a chunk of N2 ice from an exopluto. And so this makes Oumuamua a piece of an icy exoplanet and the closest such thing that ever passed by Earth. And that's it. And I thank you for your attention. Thanks very much. Be happy to take questions.
Thank you very much, Steve. That was a great talk. We learned a lot about this object. Let me tell everybody that the floor is open for questions. Please go ahead and use the Q&A button on your screen to ask or send us any questions you have, and we'll ask it from Steve. Okay, so while the audience are typing theirs, let me start by asking ours a few. So you mentioned about the local standard of rest. Can you further explain on that a little bit?
Oh, yeah. And I bring it up. It's a sort of arcane and a little bit complicated topic. It was just that it was something that was pointed to as unusual, like its speed relative to the local standard of rest was too low. So I'll go back to the slide. Go back to, whoops, hold on. Right to the 13 strikes again. I'm having trouble seeing my screen, so just give me a second. Okay, so there we go. Yeah, so we're going to go back to the first slide. We have to think about how objects are going around the galaxy, first of all. So here's the sun and its neighborhood, and all of the stars in its neighborhood are going around the galaxy, and they take 200 and something million years to do that. And the average speed as they do this is about 240 kilometers per second. So everything is moving 240 kilometers per second, give or take. And that average speed that is what we call the local standard of rest. And then when we zoom in on our own solar neighborhood, this is what it looks like. So another thing to point out is this is 8,500 parsecs between our sun and the center of the galaxy. And now we're zooming into just the nearest 100 parsecs or so. So the sun's neighborhood within 100 parsecs, all the stars we see in the night sky are in this local neighborhood. And so on average, they move with this average speed that we call the local standard of rest. But then they'll have a little bit different speed. You know, it's about 10% of their orbital velocity around the galaxy. But compared to the average, they're zipping around in these different speeds and directions. So, and typically for stars that have been around the galaxy for a long time, that speed, that random speed on top of the average speed is on the order of 20 to 30 kilometers a second. So the sun is moving at 18 kilometers per second with respect to the local standard of rest, which if it's 240 is the average, then the sun is actually moving 258. And I hope that helps. I don't want to get too much and make it too confusing.
It does. It does. Thank you very much. So here is a question. You mentioned about the N2 evaporating from the surface, and somebody's asking if traces of that are observable throughout the galaxy. Could we find maybe paths of these objects based on the amount of N2 existing in that?
Well, through the galaxy, it would just be way too thin for us to observe. And usually the question I'm asked about this is, could we have seen N2 gas evaporating from the comet itself or from Oumuamua itself? And that's, you know, when it's really outgassing and it's close by, that would be our best chance to see nitrogen ice. And it's very tricky, even in that situation, because, and in comparison, we could detect N2 coming off of that comet 2016 R2. The nitrogen molecules become ionized, N2 plus makes blue light when it undergoes its transitions. It actually fluoresces. So we can detect blue light that's coming from N2 ice. And why didn't we see that from Oumuamua? And part of the reason is we weren't looking with telescopes that were sensitive enough to those really blue wavelengths, but also it was just so small. It wouldn't have made nearly enough, even at the time we were observing it. So had we known to look for N2 ice or N2 plus molecules and used a really good telescope with filters in the blue and looked at it when it was close to the sun and vaporizing a lot, I think we would have seen it. But we have to remember this object is something like thousands of times smaller than that comet R2, and even then, it's not easy to detect N2. So, yeah, it's a really hard thing to find.
The questioner wants to elaborate more, maybe perhaps when looking at it absorption spectra as it nears the sun, would that make it detectable, the N2 gas?
Well, the easiest way to detect it would be through the emission of the fluorescence of the N2 plus molecules. Yeah.
Okay. And now, the next questioner wants to know how much is our ability to detect small objects improving? Is that significant each day? Are infrared detectors like the James Webb Telescope be useful for these kind of surveys?
Yeah, great question. What are the capabilities coming online now? In terms of detecting these objects, there's going to be a quantum leap in just a year or two. I don't know if you can hear the fireworks. There's inexplicably fireworks outside of my window. Seeing them.
Yeah, we could. So that's what they are.
Amazing. Yeah, so the Vera Rubin Observatory is an array of telescopes, kind of like the Pan-STARRS array, but with an order of magnitude better detectability. And I forget how much, like petabytes of data are going to be taken per year, just scanning the entire sky, and with a limited magnitude that's even superior to that. So if it took Pan-STARRS, Pan-STARRS abilities were able to detect maybe one Oumuamua per decade. It's hoped that the Vera Rubin Observatory will be able to detect such an object every year or so. So we'll see what the statistics look like, how many objects there are, but I think that's roughly our expectation. That will be really useful because that will allow us to characterize them better in two ways. The James Webb Space Telescope obviously is very sensitive to infrared. Right now with the Spitzer Space Telescope, the infrared detection could only place upper limits on the CO or methane. And but James Webb, if it could observe Oumuamua in the same sort of way, it probably could have detected any CO if it was there at sort of the Pluto-like levels. So that's one way for sure. And then there's also the possibility of having spacecraft visit. So if you know and can detect ahead of time these objects, then it might be possible to send an interceptor. And the European Space Agency has a mission they're planning and building towards in less than a decade from now, called the Comet Interceptor. It'll be a spacecraft that's already sort of orbiting Earth distantly, like one of the Lagrange points. If a long period comet, or better yet, an interstellar object like Oumuamua comes through the solar system again, they can send it on a path that would go near it. Obviously, you can't match speeds. If you could match speeds, we could just send it out of the solar system, but we can at least fly by at high speed and get close-up images and spectra, and that would probably really revolutionize our understanding of these objects. So these are all the things to look for in the next decade.
Okay, great. Yeah, because one of the things that was very much in the news is that somebody was complaining, why are we not sending a spacecraft as soon as we can towards that? So you do think that these kind of objects are, let's say, interesting enough for us to send something emergencyly towards them, or these European agencies' spacecraft is good enough for is enough for doing this?
Oh yeah, no, I think that I mean, obviously you can't plan a mission around something that we didn't even know for sure existed before 2017, but now that we've seen Borisov and Oumuamua, and we expect to see more of these, then it becomes a justifiable target of the spacecraft. And I think it is the most compelling possible target. This is something from outside of our solar system and a piece of an exoplanet, and we can observe it up close, and especially to get spectra and know its chemical composition would be really powerful to theories of planet formation. And I'm so excited about that prospect. Absolutely.
Okay, great. And now, yes, we have Helen has a question, please.
Thank you. Great talk. I really enjoyed it.
Thanks.
I have a question which is kind of, well, relatively speaking, you know, when we are in space and sometimes we say top and bottom and whatever, it's just what we are choosing to say. But if you could show the slide that you had up a second ago about your showing our motion in the galaxy.
Yeah.
So it looks like our star is traveling in a clockwise manner from what we're calling the top down of the galaxy, but don't the planets in the solar system go counterclockwise if we look at it from what we call the top down?
Yeah, that's a really good point. And I won't claim this is accurate because I might not have been careful, but I'm pretty sure that we're going opposite the direction you'd think about the spiral arms, or no, maybe this is the direction you'd expect based on the spiral arms. Yeah, I don't remember actually, but let's see, the center of our galaxy I do know is in the constellation Sagittarius. And that just points out that our North Pole has very little to do with where the galaxy's North Pole is. You know, the Earth's axis is different from its orbit around the sun, and the sun, you know, the Earth's orbital plane is different from you know, the plane of the galaxy. All of these things are topsy-turvy. So I've lost track of where everything is exactly. So, but yeah, this is the direction of Vega, and this is the direction of Sagittarius. That much I remember. And the North Galactic Pole, I'm trying to remember if it's, I actually don't remember where it is. Obviously, where the Milky Way isn't in the sky.
Yeah, this looks correct to me. Absolutely. Yeah.
Oh, thanks.
Fantastic talk. Very persuasive. Very persuasive. Yeah. I thought I'd be disappointed to hear someone come up with a really good explanation, but I'm actually, no, I'm happy with this. This is
Thanks
good.
very
It's,
much.
it's better than a Star Destroyer, I have to admit.
If I can editorialize, that's one of the frustrating things about Avi Loeb's book, what's called Interstellar or something, because it seems as if, well, first he's accusing any scientist who doesn't just accept that it's alien technology or something as being closed-minded. And in fact, it's really the opposite. Science always requires imagination. You have to imagine what it could be, especially when it's something we haven't seen before. But science is also about winnowing down the possibilities by seeing what works and what doesn't work. And if you haven't found something that works, you don't like immediately go to the Deus Ex Machina and invoke aliens or something. You just try a little harder to imagine what it could be. And it actually didn't take that much imagination. It was like, it's ice. Oh, it's an ice we see on Pluto. Okay, wasn't that hard. But until you kind of exhaust those possibilities, you can't really invoke aliens. But so it was a little irresponsible of him to write a whole book based on that premise. But one of the detrimental things it has done is, I think we've identified a piece of an exoplanet. This is not some random comet. This is a piece of a planet, underwent differentiation and had oceans. And I mean, I don't think 50 million years is enough time for life to evolve on a Pluto-sized object, if it ever evolved at all. But you know, we could start to imagine those possibilities, and certainly we can make predictions about things. And it's a piece of a planet, and that is just so cool. Yeah. But we can't talk about that as long as we're talking about why it isn't aliens.
True. Yeah.
I really appreciate getting to stand in the middle of a group of people doing research. And you've put us there, I think, that listening to you talk about what you and your colleagues have been working on, we're in real-time research as you're talking. And I don't think I get to do that very much. And it's important research. So it's really nice to be in on the conversation.
Thanks. Yeah. Yeah, I like my job a lot.
As well, you should.
Great, thank you very much. And now we have another question. So you mentioned the most things that we expect to be from other solar systems are comets. What about meteorites? Has ever a possibility been considered?
Oh, yes, very much. And to be precise, I think that we expect more. I think these Oumuamua fragments from dwarf planets, icy fragments from dwarf planets, to be the most common object in interstellar space. They would outnumber comets by about 2 orders of magnitude. So they're the most abundant thing. However, they're very small and they don't have a lot of dust and they don't outgas like comets. So they're very hard to see. And so in the end, we don't see more of them. And so roughly speaking, we should see about the same number of objects. Right now we have 1 icy fragment and 1 comet. But Borisov was so much easier to see that even if they're rare, we can see them from far away. And so the numbers we observe are kind of comparable. As for meteorites, like rocky pieces, yes, they should also exist. And people have thought about how to look for them. They would not be as common because probably they're coming from, in our solar system, they would come from our asteroid belt or ejected from planets, but probably more of them from the asteroid belt. But the asteroid belt is closer to the sun. It's inside the gravitational well of the sun. It's just harder to eject that material, but you could. There's also not nearly as many asteroids as there are dwarf planets. There was about 35 Earth masses of icy objects in the Kuiper Belt. But yeah, they should also exist. They'd be a lot harder to see because they'd be dark, basically. So we're looking for them. One very interesting thing that happened in the news recently is the same group, Loeb and his student Suraj, they looked through a database of bolides. This is the Center for Near Earth Object Studies, CNEOS. They have a database from satellite observations. If weather satellites or military satellites observe an object entering the Earth's atmosphere at high speed and being a bolide, they would put the numbers in a database, like here's its speed, here's its energy. And unfortunately, we can't check most of those numbers. And the ones that have been checked turned out to be mostly wrong. So the accuracy of that database is probably not good and also cannot be checked. However, Loeb and a student identified one object that came in 2014 and entered the Earth's atmosphere at such a speed it probably was interstellar. And if the speed is as reported in the database is correct, then the math does check out. It should be interstellar. This would have been an object less than a meter in size, and there's one such object over the last 20 years of observations. But here's the thing: that's about what we'd expect from the amount of dust that enters the solar system and Earth's atmosphere at interstellar sort of velocities. And so this was a surprise to me in the last few years. There's now a few dozen meteors observed by radar that have definitely come in from outside the solar system, going through Earth's atmosphere. And if you extrapolate to the size of, meter-sized objects, you could expect one bolide like that to come from interstellar space. Whether it's that particular one, we don't know because the speeds we can't check. But yeah, we are now to the point in the last decade where we can see dust and sometimes maybe a meter-sized object actually entering the Earth's atmosphere at speeds indicative of an interstellar origin. As for a meteorite, I don't know. No one's found one.
Great, thank you. And just somebody wants explicit confirmation. So this is not a starship searching for intelligent life in the cosmos?
I have no need of that hypothesis.
Embarrassing in any case, because they did leave.
But, you know, it's not closed-minded to say that, look, we have a natural explanation and there's like, why are you bothering talking about aliens? There are some aspects that had this object exhibited those aspects, we would have said, oh yeah, that's aliens. Like if it had taken a right angle turn and accelerations that couldn't be explained by any physical mechanism. You know, if it had made a beeline to Earth, I mean, there's any number of things. You'd think it would be obvious, but this thing looks a lot like a natural object. So then you have to play games like, oh, that's what the aliens want you to think. Science requires falsifiable hypotheses, and I don't know how to falsify the alien hypothesis. I can tell you whether it's N2 ice or not, and so far everything matches an N2 ice fragment.
And if they spent all that money to get here, why would they leave without, you know, looking around?
Another aspect, if it were a solar sail, as they infer it might be, because again, it had an acceleration, it was due to sunlight, they're imagining a solar sail, it would be thicker for some reason than any solar sail we'd make. Also, it's tumbling. Remember that its light curve requires it to be pointing towards the sun and, you know, edge onto the sun to reflect different amounts of sunlight. So if it were a solar sail, it was a broken solar sail. Explain that. I don't know.
I always recommend that people like that read Carl Sagan, Demon Haunted World.
Yeah, that's a classic. I agree.
Now that I've spoiled that. I don't know. It sells books and gets people to pay attention. So that's why people say it. I had a brother like that, and he was grossly ignorant, but always wanted attention.
Yeah.
It's a problem. The alien hypothesis does sell, and it gets you on the Tonight Show.
Yeah.
But it's not good science. Not yet, at least.
I agree.
So thank you very much. And since we were talking about the location and the direction of the motion, and it's a little bit off topic, but since it was just released, the picture from the supermassive black hole from the center of our galaxy, can you speak to that a little bit? And also, apparently its axis of rotation is off the poles towards us. So would appreciate if you talk to that to us a little bit also.
Oh my. Well, I didn't know about that. I worked on my master's thesis back in 1991 on the disk of dust and material about a parsec away from the black hole. So outside of that donut-shaped thing. But it's been a long time since I've thought about this. But yeah, certainly there is a black hole at the center of our galaxy. It's got a mass of about 2.6 million solar masses, as I recall, which sounds like a lot, but the largest black holes at the centers of galaxies approach 1 billion solar masses. So we have a tiny black hole at the center of our galaxy, but it is a natural outcome of galactic evolution. You just have a bunch of stars crowded together, and at some point they collide, merge. You just have too much material in one place. It forms a black hole. I don't know if I know that much more about it, though. I can tell you, but yeah, we knew about the black hole from the orbits of stars that could be observed. There are certain stars that are orbiting every 10 to 20 years at a distance of a parsec away or so, and there just had to be millions of solar masses in there.
Great, thank you very much. And as the last question, can you tell us a little more what is next about this Oumuamua object? Are we done with it, or and we are looking forward to new objects, or still research can be done as it's getting farther away from us?
No, yeah, it's already, I think, past the orbit of Uranus by this point. It's moving really fast. So After it was 2 AU away, the Spitzer Space Telescope and Hubble Space Telescope's observations, just a month after it was discovered, that was the last opportunity we had to observe it. It's just way too faint. It's, again, remember, it's something the size of a football field, and we just can't see it very far away. The next big thing is to find more objects like this using the Vera Rubin Observatory. I want to see if we can determine whether some are water ice versus N2 ice, as we've predicted. Hopefully see more N2 objects. Definitely see if we can detect N2 plus emission from one of these objects outgassing. That would clinch this. But I hope we do that, and hopefully eventually an intercept mission.
Great. Again, thank you very much for a wonderful talk. We really enjoyed it. Thank you very much.
Thank you, Don.
Thank you.
Before I end the meeting, do you have any final comments you would like to make, Steve?
No. Thank you very much, though. It was a really great audience, and appreciate all your questions. Had a lot of fun. Okay.
Great. So before I end the meeting, let me remind everybody that you could check our the calendar on our website for all our upcoming events at ocastronomers.org. Thank you all for joining us, and wish you great times ahead. Bye-bye, everybody.
And I'll go to the other Zoom link now.
Right.